Hello, my name is Alexandr Mordvintsev, and today I'm going to talk about differentiable self-organizing systems on the example of neural cell automata model. Self-organization is omnipresent in nature and can be vaguely described as capability of a system to maintain order and structure or reach some goals through local communication between tiny little parts that constitute this system, whether those parts are molecules, cells, or individual organisms. Building their own bodies is the very first skill that every living creature possesses, and it can be seen as one of the most striking examples of self-organization. I'd like to make today's presentation in the form of a live coding session, where I'll show how to implement the growing neural cell automata model from our recent publication from scratch. I'll try to show some tiny details and interesting experiments that didn't make it to the paper, and we'll try to replicate the behind-the-scenes process of development of this model. Before proceeding to coding, let me show a little video clip that hopefully explains the concept of differentiable self-organization and neural cell automata. Generally speaking, differentiable self-organizing system consists of a neural controller that is shared by a population of agents interacting on a simulated environment during a limited time span. The whole system is evaluated against an objective function that measures the proximity of the current behavior to the desired. End-to-end differentiability allows propagation of the objective gradient to the controller, steering the system behavior towards the target specification. Neural CA operates on a uniform grid. The state of each cell is represented by a number of real values, 3 of which are visible as RGB color channels. Cells iteratively update their state using the information collected from their 3x3 neighborhood. Now we are ready to build a model that will grow a predefined pattern starting from a single seed cell. I will be using Google Colab environment for our experiments, and here is a fresh new notebook that I've created. First of all, let's make sure that we are using GPU accelerated virtual machine, and double checking that we have an accelerator. Yes, we've got Tesla V100 here. You may notice that I'm using a paid pro version of Google Colab, otherwise I'll be getting K80. A paid version costs around $10 a month. Now let's set up some boilerplate. I'll be using a feature of Colab that's called code snippets. This list contains a lot of useful little pieces of code that can be copied in the current notebook, and also this list can be populated by user by adding links to notebooks that contain custom snippets into this list at settings dialog. So I'm copying the cell that contains a bunch of image manipulation functions and video recording class that I'll be using extensively during this presentation. Let me execute this cell and collapse it so it doesn't occlude the view. Let's remove unnecessary cells, and now we are ready to go. Let's load the target image that we will train our cell automata to grow. I have a secret second window that I'll be copy-pasting some pieces of code from, so that you don't have to wait while I'm typing them. So here is our lizard that is going to be our target, and we will grow a pattern of size of 40 pixels. Well, two small patterns look too ugly, and big patterns require more time to train, more cell automata iterations to grow, and maybe bigger models converge slower, sometimes don't converge at all. So 40 seemed to be like a reasonable number for demonstration purposes. And also I'm copying a little helper function that loads emoji by pulling the corresponding PNG from GitHub repository from Noto fonts. So let's load the image and display it. Yes, our image loading works, and you may see that our lizard is a little bit different from the one that we use in the original article, and the reason is that since we published the article, Android updated their lizard emoji, so we will grow a new emoji. And one helper function that I'm using during this presentation is zoom. That is a helper to zoom images conveniently. Also, sometimes it's handy to display outputs of a cell to the right of it rather than below, to make the code and output stay side by side. One little detail that we need to be aware of, this is pretty subtle, is the fact that the lizard image is a 4-channel image. It has alpha mask, and if we independently look at RGB channels, especially if we zoom it a little bit, then we will see that there are some pixels that don't belong to non-transparent part of the image, and if we match the output of our cell automata against this, our loss will also account for those unnecessary extra pixels. So I prefer to store the image in premultiplied format. So I am premultiplying RGB channels of image with the alpha channel. By the way, alpha channel looks like this. So I'm premultiplying the RGB part with alpha to get a premultiplied target image. And this image looks, you may notice that it looks a little bit darker at the edges because now blending works incorrectly, and I'll use a special dedicated function to display those premultiplied RGBA images. This, I'll call it 2RGB, and now if we use this function we will get original correctly rendered emoji, although it's stored in a premultiplied alpha format. Now we've defined the visual shape of the state that we want our system to arrive. Time to define the initial state and also the data structure that is going to represent the state of the cell automata at every iteration. Each cell is going to store some amount of information. Obviously we need 3 values to represent RGB colors, but it's necessary for cell to store some internal representation of its position inside of the grown shape. So we will use the value of 16 channels. This value is pretty arbitrary but seems to work reasonably well. So let's define the initial state of the grid. The grid is going to be mostly filled by zeros, and we use the defined shape, specify the number of channels, and so all grid is going to be filled with zeros, but the one cell in the middle will have a special value. Note that I kept the first 3 channels to 0 value because I want the black dot to be visible on white background, given the way we visualize images on screen. Now we're ready to build the first version of neural cell automata model. Here I'm copy pasting it, and as you see, it's quite simple. It's built out of convolutional layers only, exploiting the close relationship between convolutions and cell automata. Namely, convolutions are cell automata that restrict the operation they perform to a linear function of the cell's neighborhood. The first layer models the perception of a cell and projects 3x3 neighborhood of each cell into 128-dimensional vector, also applying linearity so that we have some nonlinear components in our cell automata so that it could learn more interesting functions. And the second layer just computes independent per cell update vector that is being incrementally added to current state of each cell. We use incremental updates being inspired by residual networks and Euler integration of systems of partial derivative equations. Let's see what would happen if we start from our seed and iterate the model for a few steps. Here is the result that we got after running a randomly initialized neural CA for 20 steps. If we run this cell again, we will have a different image, because we are instantiating the cell automata on each cell execution. Let's visualize the whole process of cell automata evolution from a seed rather than the final iteration. Let's give it a few more iterations. Each time we run this cell, we get a different behavior of a cell automata. And there are a few interesting things to observe here. First of all, the development starts from the seed cell while the background stays constant at the early iterations. And the reason for this is the default initialization that Keras library applies to convolutional layers, namely it uses zeros for initializing biases. Together with zero initialized background, it prevents cells from changing their state until the wave from the seed reaches them. You may notice that the model we implemented is much simpler than the one we used in Growing Neural Cell Automata article. In particular, we don't use stochastic updates or live masking, and we use the fully learned convolution to model perception instead of this combination of fixed 3x3 convolutions and 1x1 convolution we use in the original article. We will discuss those changes a bit later, but now it's time to train something. First of all, let's estimate the number of parameters that our model has. Our model has 20,000 parameters, and this is relatively small by current deep learning standards, but relatively large for a neural cell automata. For example, all models from Growing Neural CA article have about 10,000 parameters, and the way we achieve that is by factorizing the perception into two parts, one of which is a fixed convolution and another is 1x1 convolution. I'm going to write some training boilerplate. I'd prefer to explicitly define the training loop myself, so that I have the full control on what's going on and on visualization of the training progress. So let's start with defining the loss function. I'll begin with 50 iterations of cell automata because it's supposed to be enough to grow the pattern of size of 40 pixels. And after 40 iterations, we expect the first 4 channels of the grid to be equal to the target pattern. We use per pixel square differences and average them across all pixels. We are interested in computing the gradient of the loss over the cell automata parameters. We have gradients, let's create an optimizer to use them. Let's run this code in a loop to see if the loss is going down. I'll now reorganize the code to make it more efficient and visualize the loss in a plot. I want to see the evolution of final states of the grid during training as we see now that in spite of loss going down, the final state of a grid still hardly resembles the target pattern. And there is a simple reason for that. The initial behavior of our cell automata already produces some complicated pattern on a grid that has very strong activation values, and what optimization is currently doing is fighting against this default behavior. There might be a few ways to resolve this problem, either to use smaller number of cell automata steps at the beginning of training, a little bit like curriculum learning. Maybe playing with optimizer parameter helps, but the simplest solution that I've found is just initializing the coefficients of the very last layer of cell automata to zeros. We now see that this makes the do-nothing behavior the default one, although non-zero coefficients at the first layer allowed to train. So let's run the training loop again and see what would happen. Now we see the lizard-like pattern is quickly emerging on the grid. Let's train for a few more hundreds of steps. One thing that bothers me at this loss plot are those sudden jumps of loss while training. Let's try to investigate why they happen and how to prevent them. I've experimented with a number of approaches to reduce those spikes, but the simplest approach I found was based on the analysis of gradient magnitudes during training. We see that those spikes in the loss seem to be aligned with sudden jumps of the gradient magnitude, which seems to interfere with Adam optimizer, so I decided to normalize the gradients to stabilize the training, and it seemed to work somehow. Training seems to be more stable. There are still some little jumps, but what I've noticed that while in this experiment this gradient normalization wasn't particularly critical, in some other experiments that I've performed it was very hard to train a model without normalizing gradients during training. After 2000 training steps, the model is in a pretty good shape already, looks almost like an original lizard, so let's play a little bit with the cell automata we've created. We see that the model produces a pretty good lizard at shape around step 50, but then the pattern degrades and gets completely destroyed because there is nothing in our loss function that makes it stable. All we are asking for is particular pattern at the step 50. Before trying to stabilize the cell automata at particular pattern, I'd like to talk about yet another important detail of our neural cell automata model. As I've told, we don't use stochastic update yet, which means that all our cells make updates at the same time at each iteration, which implies that there is some global synchronization mechanism between them. In order to call the system self-organizing, I'd like them to be as decoupled as possible. So I wanted to have a model that doesn't rely on existence of this global synchronization mechanism. One way we can try to achieve this is by stochastically updating only a fraction of cells at each iteration. Of course, this is only one of the possible asynchronous computation models. Another interesting idea to explore may be wave-like spreading updates, such as, for example, on this video of bees shimmering. There are many ways to explore to make those differentiable self-organizing models more lifelike. Let's implement the stochastic updates. This code produces the mask of ones and zeros, and 0 and 1 have probabilities of 1.5, and we produce only one value per cell. So those masks are per cell but not per cell channel. And we multiply the update vector by this mask. Cell automata now will need more steps to build the pattern because each cell fires only half of the time. So we give it 100 steps. I will also modify the training schedule by decaying the learning rate at step 1000. Let's see how it trains. It seems to be a little bit harder for the model to generate an accurate pattern in this regime. Let's try to increase the batch size from 1 to maybe 4 instances at each train. After 1.5 minutes of training, we see that the loss variance is lower now, and we arrived at better solution, whilst the loss is still decreasing. Let's have a closer look at the model we've created now. I will make a helper function so that we use it to experiment with putting our model into various conditions not seen during training. The first video shows the evolution of cell automata during its normal operation, and we see that it decided to paint the background green at the intermediate steps for some reason, although eventually it arrives into a normal state. And the reason for this is that we don't impose any constraints at the behavior of the background cells during operation, and they are all allowed to participate in the computation at all steps. The second video shows the evolution over a longer number of iterations, and we see that the pattern that cell automata constructed is not stable, and it starts to decay after iteration number 100. And the third video demonstrates operation of our cell automata on a larger grid over a course of 100 steps, and we see that on a larger grid, the cell automata constructed a pattern that is not entirely correct. The tail is longer than expected, and the head is a little bit of a wrong shape. And the reason is that our cell automata overfitted to detect boundary. It knows that there are cells outside of the grid that are always zero, and looks like it relies on their presence to learn where to stop growing the tail. So once we push this boundary further, the tail extends further. I will try to address the stability issue first. The naive way to do that would be to introduce an additional loss that will penalize the changes of the grid after a certain number of steps. Let's try to do that. Let's run training. The step 2000 loss is still going down, but let's look at the stability of the solution we found so far. So running cell automata for 300 steps, and we see that first it produces the pattern, then it maintains it for a while, but then it starts to slowly decay, probably much slower than without the stability loss, but still pattern is not stable. Let's try to train for a couple thousand steps more. So training is completed now, and we can visualize the behavior over 300 of steps again. Well, the pattern seems to be more stable, but then it finally starts to decay. We may spend some time tuning the weights of those two losses, the stability loss and the target loss, but in my opinion it complicates things, adds additional coefficients. We found a different solution to pattern stability problem. Rather than trying to add additional loss terms, let's formulate the optimization problem a bit differently. We need a cell automata that can produce the target pattern if it receives the grid with the seed in the center, or if the grid already contains the pattern at some stage of growth. So we will create a pool that will contain a set of states of a grid, and then we will sample states from this pool, let cell automata evolve those states, backpropagate loss over a fixed small number of steps, and then put the resulting states back to the pool. We initialized the pool with seed states, and also we want to add a seed to each training batch so that the cell automata doesn't forget how to grow from the initial seed state when the pool gets populated by semi-finished or finished patterns. Let's visualize both initial states for a batch and the final states. Little by little, the model is learning to grow from the starting state and preserve or even improve, like here, pattern if it's already there. Let's give it a couple of thousand steps more. After 4,000 of steps, the model grows and maintains a nice lizard, and let's see its longer term behavior. 300 steps. Okay. pattern seems to be stable. Let's make another test. Let's run the model over, say, 1,000 of steps and draw a loss plot over those iterations. So we see that loss goes down quickly at the beginning of cell automata evolution and reaches minimum around the step 100, and then unfortunately grows little by little. We'll try to figure out what's going on and how to fix that. So here is a visualization of the cell automata state after step 1000, and we see that there is some spurious accumulation of values that's probably happening in the background cells. And another out of training behavior I want to investigate is the behavior on the larger grid. And here we see a pretty interesting phenomena happening. We see that the model fitted to use grid background to determine where to grow the tail and the head and a part of a leg of a lizard. Now let's think about ways of fixing that. In the growing neural CA paper, we were using the technique we called alive masking, when only cells having alpha greater than 0.1 or their neighbors were allowed to participate in the computation. The state of all other cells was reset to 0 after every cell automata iteration. Let's try to implement this technique here. The variant of the technique implemented here is a little bit simpler than the one described in the article, as we only used the state of the grid before the update, but this shouldn't cause big difference in the results. To reduce the chance of touching the grid boundaries while growing, I will also pad the target pattern with empty space. I have also modified the training schedule a little bit. Now we can start training again. So after training for around 6,000 steps that took 10 minutes, our model learned to grow the pattern. And what's interesting, that if we draw a plot of the pattern accuracy, like pattern quality over cell automata iteration, we see that the best quality is achieved around iteration number 300, which is way outside of the number of steps that we perform backpropagation through. So the model learned to iteratively improve over the existing solution. Unfortunately, this particular variant still displays some instability. I don't know right now what is the cause, but we didn't implement all the pieces from the original model. For example, we still don't use this factorized perception. Maybe that's the reason, but I think this little tutorial demonstrates the process of building a neural cell automata model from scratch. I'll publish the code on GitHub, and hope you enjoyed this presentation. I'm ready to take your feedback and questions. Thank you for your attention.